He's working on his fifth. And so now math is his bread and butter. You never can tell where you're going to end up. So you never can tell what's useful and what's not. Okay, so 4.1, we now reap the benefit of all of the rules that we have been inducting from the definition of the derivative. That, yes, of course, you need to know that the derivative of x is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And we've done several problems like that. But therefore, from this, and on the midterm you're going to have two problems, you've got to work that from that definition. We now have, from this, patterns. And once you have the patterns, it's so much easier to work with. That's what we're going to do now in 4.1. And before I do these homework problems, let me just summarize. I don't know. Yeah. So the book has introduced this notation. And I don't think I've used it before, but let me use it now. Derivative. Extremely important concept, runs throughout all disciplines, including in special economics. And you shouldn't be surprised that there's more than one notation for it. df over dx is the same, is the notation for the same thing. You might say, why? Well, this notation, the prime mark, that's easier to write than df dx. But the advantage of this notation is that it reminds you at every step what the independent variable is. Now in your problems we only had one variable, so there's no ambiguity, but soon there will be. So each of these notations has their own definition, has their own advantage. But in order to sum up some of the patterns now, we've seen that the derivative of a constant is 0. And we've seen that the derivative of, if you got some coefficient m times x, the derivative is just m. Coefficients stay. And the derivative of x is just 1. Then we've got this power rule. Say if you got a coefficient of k, and you've got x to the nth power. Well, the coefficient stays. The old power becomes a new coefficient. The new power is 1 less. So we've been evolving these patterns from our definition. And then on Monday, I just threw in a couple of more. The book gives you these without proof. I could prove them to you, but I think you'd rather I not. E to the x is the funny function that is its own derivative. That's really, e is the only number that'll do that. E is this funny, non-ending, irrational number. It's the only number that will give you its own derivative. And then we also talked about, the log function was very important to us. A couple weeks ago we did a lot of problems with log function. The derivative of the log is 1 over x. So I think that summarizes the patterns that we've been involving in chapter 3. And now we use these things. Problem 1. F of x is 13. That's that pattern. 13, it's not 13x, it's just 13. It's just constant. In which case f prime is 0. Another way to look at it. We've said the derivative is the slope of the tangent. That's a useful thing to remember. We have said that the derivative is the slope of the tangent. Well, think about what that means in this case. If you've just got f equals 13 or y equals 13, don't you know that that's a horizontal line up here at 13? So the tangent to a line is itself. The tangent line to a line is itself. And so you know the slope of a horizontal line is 0. Right? Slope of a horizontal line is 0. And the tangent to a line is the line itself. So its slope is 0. It all hangs together. Oh, and number 3, don't let that fool you. F of x is equal to e plus pi. And in fact, don't let him fool you here. In fact, I might do this to you on the midterm. I think it's question, can't remember the question. There's a study guide, they'll show you this. It's a 3-point problem, I think it's question 5. I will ask you to use some of these patterns. The problems are intended to be easy, but I'm going to throw you a curveball. Remember, E itself is merely a constant. Pi is merely a constant. So you're adding together two constants. And remember what we said? The derivative of any constant is 0. Now, you might say, okay, E, it's e to the x, which is its own derivative. When e is alone, it's just 2.7. It's just a constant when it's alone. There are no x's there. So they're constants, so the derivative is 0. And I could do that to you. Oh, here's another one. This is for free. E to the pi. Don't let it fool you. There are no x's there. It's not a function. It's just constant. The derivative of e to the pi is 0. It's still just a fancy constant. There's no x there. No x, no function. All right, now, problem 5. Here we get into our patterns. So our f of x, we're told, is x to the 23rd power. So f prime, the derivative, what is our power rule? The old coefficient, the old power is a new coefficient. The new power is one less. Done. There's your derivative. 7. That's 1.4. F of x is x to the 1.4. Now, I know that we've only done this for integers. Our pattern was x to the n, so f prime. The old power is the new coefficient, the new power is one less. We've only done n for integers, but indeed it works for all numbers. So in this case, the 1.4 is a new coefficient. The new power is 1 less. So 1.4 subtract 1 is 0.4. The old power is new coefficient. The new power is 1 less. Same pattern, even if it's not an integer. Number 17. Here our f of x is 2 e to the x minus 1. Okay. Well, let's put our rules, our patterns together. 2 is a coefficient, so it stays. The derivative of e to the x is e to the x. That's the funny number e. E to the x is its own derivative. And the minus 1, that 1 is just a constant. Its derivative is 0. So this derivative is e to the 2x. (19) f of x is pi x plus twice the log of x. Okay. Now here, pi is a coefficient, and a coefficient stays. So our derivative, pi is the coefficient of x. It stays. The derivative of x is just 1. Remember that pattern, just to review? If I've got x, well, that's the same as x to the first power. And so what's our power rule? The old power is a new coefficient. The new power is 1 less. But 1 subtract 1 is 0. Anything to the 0 power is 1. 1 times 1 is 1. So the derivative of x is just 1. And as long as I'm talking, do you see how all this fits together? If my function is y equals x, that's the 45-degree line, right? And the tangent to a line is the line itself. The 45-degree has slope 1. So it all hangs together. Plus, haven't finished here. 2 is a coefficient, it stays. Log x is 1 over x. Are we okay? That log is just one of the derivatives that they gave to you. And just in passing, forgive me if I'm insulting some of you, but 2 years of COVID have left some of you with shaky algebra. So is this okay? 2 times 1 over x is the same as 2 over x? Some people struggle with stuff like that. Are we okay if you've got 2 times 1 over x? 2 is the same as 2 over 1 times 1 over x. And when you multiply fractions, what do? You multiply the numerators, you multiply the denominators. Just in case some of you are a little rusty on your algebra. And as long as I am digressing, boy, this comes up a lot. Let's start with arithmetic. If you've got 2/3 plus 1/5, Remember, you can only add fractions if they have a common denominator. So this denominator is 3, this denominator is 5, the common denominator is 15. So what you have to do is you take this 2/3 and you multiply it top and bottom by 5. And you take this 1/5 and you multiply it top and bottom by 3. Now they have a common denominator of 15. Now you can add the numerators. 10 plus 3 is 13. So most of you feel insulted when I do this. However, this is what's going to come up. All of a sudden we're going to have fractions where we've got letters or variables. And the same jazz applies. The only way you can add fractions is if they have the same denominator. The common denominator is b times d. So what you do, multiply the first fraction, numerator and denominator, by d. The second fraction, multiply it numerator and denominator by b. And so now the common denominator is bd, and your numerator is ad plus cb. I mean, I hope that you are all bored. You know what I get though? You can't just add denominators. It doesn't work. Look up here. Would you do that up here? 2 plus 1 is 3. 3 plus 5 is 8. No. So, as I say, this is going to come up. Now let's look at 21. And I sure hope that you've taken time to at least try these on your own. The worst thing you can do in a math class is come to class, take notes, and try to memorize it the night before. Guaranteed F. You got to work this stuff into you. So 4 minus x squared. Let's use our patterns. 4. It's not 4x, it's just 4. It's a constant. Its derivative is 0. The derivative of x is 1 and you're subtracting it. The derivative of x squared is 2x and you're subtracting it. So your derivative turns out to be negative 1 minus 2x. Number 25. Put them all together. So here they give you 1 minus x squared minus x cubed minus 10 log x. Okay, we'll do it term-wise. 1 is a constant. Its derivative is 0. The derivative of x is 1 and you're subtracting it. The derivative of x squared is 2x and you're subtracting it. The derivative of x cubed? 3x squared. 10 is a coefficient, it stays. The derivative of log x is 1 over x. And I'm perfectly happy if you leave it that way. I just want to emphasize, 10 times 1 over x it's the same thing as 10 over x. You don't have to write it that way, but some people don't understand. Number 31. So here we have f of x is equal to e to the fourth. Don't let them trick you. That's not e to the x. That's e to the 4. There's no x there. That's a constant. Minus log x minus 0.01x squared minus 0.03x cubed. So the derivative. Don't let the 4 fool you. It's just a constant. The derivative of log x is 1 over x. Don't let the decimals throw you. Lots of things have got decimals in them. That 0.01 is just a coefficient. A coefficient stays. X squared goes to 2x. This 0.03, it's just a coefficient. It stays. X cubed is 3x squared. And so if you do your arithmetic, negative 1 over x minus 0.2x minus 0.09x squared. Now, let me belabor this point. E to the 4. Are we agreed that's a constant? The way you can spot a constant is because there's no x there, or t, or whatever your variable is. There's not a variable there. It's e to the 4th. So that's why the derivative of any constant is 0. And that leads me to say the following. So we have a couple of patterns here. These are good patterns. If you want the derivative of x to the n, it is nx to the n minus 1. If you want the derivative of e to the x, it is e to the x. But now I'm going to take my red pen, because this mistake happens a lot. They forget that e to the x is like a special case. They try to apply this pattern to this problem. And they say, okay, the x comes down in front, the new power is 1 less. Do you see what's wrong? In our pattern here, the variable is x in the base. The constant is the power n. And that's the derivative. But you see here, x is the power. Your variable is not in the base. Your variable is not in the base. Your variable is up in the power. And so you can't do that pattern to e to the x. But I would say that's a very common mistake. Because you get this so ingrained in your head that you try and do it to that. And it doesn't work. Yeah, what I'm thinking. I'm thinking about showing you this because it relates to compounding interest continuously. But I don't think, I'm not sure it'll speak to you. Let's do 35. Here we have f of x is equal to 3x squared plus 3 over x. Did I say? I misspoke. 3x cubed. I miscopied the problem. It's 3x cubed plus 3 over x cubed. This is a good problem because this pattern and this pattern are a little different. What I need to do is I need to remind you, when you've got the x cubed in the denominator, do you remember that negative powers mean reciprocal? The way to handle the derivative of 3 over x cubed is you have to recognize that that x cubed in the denominator is x to the negative 3. So remember about negative powers. If you've got a to the negative 1, that's 1 over a. If you got a to the negative 2, that's 1 over a squared. So here I have 3 over x cubed. The only way to invoke your pattern, we're going to invoke that pattern now, is to write x to the negative 3 because n, this works for all n, whether it's fraction or negative. So now the derivative becomes 3 is a coefficient, it stays. X cubed, the old power is a new coefficient, the new power is 1 less. 3 is a coefficient, it stays. The old power is a new coefficient. The new coefficient is 1 less, and don't forget about your negative numbers. If you do negative 3 subtract 1, that's negative 4. People sometimes put negative 2 there because they forget about negative numbers. Negative 3 minus 1 is negative 4. So this is 9x squared minus 9x to the negative 4. It's perfectly fine if you leave it that way. I'm only doing this for emphasis. I'm just trying to emphasize to you, if you've got x to the negative 4, what does the negative 4 mean? The negative power is reciprocal, and you're dividing by it. Yeah, and number 43, we have it in spades. F of t equals 1 over t plus 1 over t squared plus 1 over t cubed. Now, the book really likes to play around with different names for the independent variable. But generally in practice, all you ever use is x or t. This I'll keep t as a frequent independent variable. It stands for time. Very often stands for time. Now, before you take a derivative, what you need to do is you need to recognize the negative powers. Your powers here are negative. 1 over t is t to the negative 1. 1 over t squared is t to the negative 2. 1 over t cubed is t to the negative 3. Now that's algebra. I haven't done anything yet. I haven't taken the derivative. Sometimes people stop there. I mean, the algebra is correct, but don't stop. Because the question now is take the derivative. So you've only turned those into powers. Now use your power rule. The old power is the new coefficient, the new power is 1 less. Don't forget about subtracting negative. Negative 1 minus 1 is negative 2. The old power is a new coefficient. The new power is 1 less. Are we okay? Negative 2 subtract 1 is negative 3. Plus. The old power is a new coefficient. The new power is 1 less. Negative 3 minus 1 is negative 4. Now, there's nothing wrong with that answer. If you left it like that, I'd be happy. I'm only saying this to be sure you're comfortable with the algebra. So you don't have to do this last step. You need to understand the last step. Are we okay? If I've got negative 1t to the negative 2, that means I got a negative 1 in the numerator and I got a t squared in the denominator. Now here, with the negative sign out in front, 2 is in the numerator, t cubed is in the denominator, because this is t to the negative 3. Here I subtract, 3 is in the numerator, and I have in the denominator t to the 4th. So you could leave your answer there, but I want to be sure that you understand. Be sure you understand about negative powers. I really hope I'm boring you. I really hope that all of this is just remedial review. That would make me happy. I think I've said it before. In math, there are only 2 emotions: boredom and terror. If you understand, you're bored. If you don't understand, you're terrorized. So, number 45. Here we have f of t is the cube root of t minus 1 over the cube root of t. Okay? Do you remember fractional powers are roots? Fractional powers are roots. So f is really t to the 1/3 power minus. Okay, now here, maybe I'll do it in 2 steps. It's 1 over t to the 1/3. So, cube root is what I mean by a fractional power, t to the 1/3. And here I have t to the 1/3 in the denominator. But before I take the derivative, what is a negative power? It's a reciprocal. Are those rules okay? What I'm doing there is just algebra. Don't stop there. Some students stop there. Well, you haven't taken the derivative yet. All you've done so far is to put it in power form. Remember our pattern. Power form says the derivative of x to the n is nx to the n minus 1. We're simply taking our given problem and putting it in power form so that we can now take the derivative. See, the problem is people stop there. They think they're done. No, you haven't found the derivative. You only put it in power form. Now we do the derivative. So the message here is that n can be a fraction, positive or negative. All n's work. So t to the 1/3. The old power is new coefficient. The new power is 1 less. How are you with subtracting your fractions? Right? Remember, 1/3 subtract 1. That's what I'm doing here. 1/3 subtract 1 is negative 2/3. Minus. The old power is a new coefficient, negative 1/3, t to the negative 4/3. Is that okay? If you've got negative 1/3 and you subtract 1, isn't that negative 4/3? And so if you left your answer like that, I'd be happy. But I want to be sure you understand. This is a 3 in the denominator. The negative puts t in the denominator. But what is 2/3? It's the cube root of t squared. This is a perfectly acceptable answer. But I want you to understand what it means. The negative puts it in the denominator. The third means cube root of t squared. Here, minus minus is positive. And here in the denominator, you have 3. Notice the negative 4/3. The negative means you're in the denominator. The third means cube root of t to the 4th. Okay? So you may stop there, but you need to understand what those powers mean. Okay. Problem 79 is a lot of language for easy derivatives. But they're just trying to give you a taste for why you're doing all this. So, okay. Marginal cost, marginal revenue, marginal profit. And I've already said that marginal means derivative. So in 1997, Fuller and co-workers at Texas A&M University estimated the operating cost of a cotton gin plant of various sizes. A quadratic model of costs in thousands of dollars for the largest plant is given by, here's your cost function, C of X is 0.02668 x squared plus 21.7397 x plus $377.3865. So this is supposed to be an actual model, where X is annual quantity of bills and thousands produced, if average projection is most 50,000 bills. Revenue is estimated. Now revenue is easy. That's saying that you can sell each bale for $63.25. And you are selling X of them. So they asked for marginal cost. And do you see why marginal cost is the derivative? Your cost function is some quadratic function. Okay? If that is your current production level, so X is your current production, C of X is the cost. Marginal cost is, if that's your production level, marginal cost is the cost of producing one more. So the cost of producing one more is giving you the slant of a secant line whose delta X is just 1, meaning it is really, really close to the tangent. So they use the slope of the tangent to estimate marginal cost. And so that's the derivative. Take the derivative here. You've got this ugly coefficient times 2x plus that there's just a coefficient that stays, derivative of x is 1. And of course that is just a constant, its derivative is 0. So there's your marginal cost. Your marginal revenue, well that's pretty easy, 63.25. Coefficient stays, the derivative of x is 1. And now what they want is marginal profit. Okay, you know that profit is revenue minus cost. And therefore marginal profit is marginal revenue minus marginal cost. You can take the derivative term-wise. That's what we've been doing. And so therefore your marginal profit is that subtract that. So they wanted to give you an actual economic model of something. So that's why the numbers are icky. On the test, you do not have your calculators. Were I to give you this problem, which I wouldn't, just leave it that way. You don't have your calculators. So just go ahead and leave your answer unsimplified. Of course, I won't give you something that obnoxious. Okay, so 4.1 was pretty short. I just scheduled one day on 4.1. And indeed, the only 3-point problem on the test is where you whip out 3 of these. 4.2. Yeah. For now, I'm just going to give you these patterns. So new section 4.2. Here are new patterns. And you can get these from your definition. So all of the patterns that we were doing in 4.1 were patterns that had come out of our definition. And here are a couple more patterns. Next time I'll prove one of them, but it's more important for you to be able to use them. This is something called the product rule. And it says, let's say that you've got two functions, P and Q. And you want the derivative of the product. Well, here's what you do. You take the derivative of the first times the second untouched, plus the first untouched times the derivative of the second. Sometimes people mistakenly think that the derivative of the product is the product of the derivatives. No, life is harder than that. This is called a mixed product, and it's a pattern that crops up a lot, meaning if you've got some things multiplied, do it to one factor at a time and then add them up. That's what's called a mixed sum, a mixed product. And that's a pattern that crops up a lot. How about a quick example? Let's take x squared plus x plus 1 times 7x minus 5. Okay, now sure, you could multiply that out the long way. But it's easier if you just do the mixed product. In other words, you want the derivative of the first times the second untouched plus then the first untouched times the derivative of the second. Now, when you're doing this, you wouldn't write out that step. I'm just trying to show you the instructions. You would write out 2x plus 1, second factor untouched, plus first factor untouched, times the derivative of the second factor. How about another one quickly? Let's say you have 7x squared minus 5x plus 1 times e to the x. Well, take the derivative of the first factor times the second factor untouched plus the first factor untouched times the derivative of the second. But remember, the derivative of e to the x is e to the x. The derivative of e to the x is e to the x. Okay, now that means you can do, we haven't done quotient rule. So on Friday, we'll talk about quotient rule. So what that means is you can do 4.2, you can do through 11. So for Friday, work through 11, those are all product rules. And we'll do those Friday, see you Friday.